In this video, we are going to talk about the mechanism of lysozyme catalysis. Lysozyme cleaves glycosidic bonds in a polymer of N-acetylglucosamine residues connected via beta-1,4 glycosidic bond to N-acetylmuramic acid residues. And muramic acid residue is pretty much the same as N-acetylglucosamine residue, just the hydroxyl group at its third carbon atom is actually modified with a lactic acid residue, right? So here we have the whole lactic acid residue labeled as R for easier drawing of the intermediates in this mechanism. So what happens in the mechanism? Again, this is the bond that is going to be cleaved, beta-1,4 glycosidic bond, right? And it's going to be cleaved because one of the catalytic residues here, glutamic acid residue, is in its protonated form, so it can act as an acid. So we are going to take the proton using the electrons of this glycosidic bond, and of course oxygen will be now negatively charged. So as a result, I'm going to draw it right here down. As a result of the first step, one of the products will already be leaving the catalytic site of the enzyme, and this product will be the part of our substrate which has N-acetylglucosamine residue at the end, right? But what happens with the second part of the substrate? It will form an oxonium ion, right? Because here this carbon will be now positively charged, correct? But in the original structure, this carbon is sp3 hybridized, right? But when the bond is broken and the carbon is assigned a positive charge, it's going to be sp2 hybridized. So we need to actually convert this chair conformation into a half chair with those 4 atoms lying in one plane, because sp2 hybridized atoms have planar geometry, right? And so I'll need to modify my original drawing a little bit, showing that those atoms are actually planar, right? So here we'll have positive charge. And of course, I need to still show all other parts. So I'll have OR here, NH acetylated amino group here. And those 4 atoms are planar now, right, in this oxonium ion intermediate. And in another resonance structure, I will have oxygen positively charged, right? So what happens with the catalytic side chain? I will still have negatively charged aspartic acid residue here, right? Because it didn't participate in the reaction. Sorry, you cannot see it, right? I need to move it closer a little bit. Aspartic acid residue will be the same. Glutamic acid residue will be deprotonated, right? So now there will be a catalytic next catalytic step, which will involve nucleophilic attack of the negatively charged carboxyl group of aspartic acid at this electrophilic carbon atom. So as a result, we'll need to go back in the chair conformation, right? Because here I will actually have the new glycosidic bond formed, and it's going to be between N-acetylmuramic acid residue and the aspartic acid residue of the enzyme. Of course, I need to continue drawing. Here I'll have OR, here I'll have another glycosidic bond, and finally OH group here. So after that, and I need still to draw the structure of glutamic acid residue here. After that, I need the help of water. And it's going to serve as a nucleophile now, but in order to increase the nucleophilicity of water, it needs to be converted into hydroxide ion. So we are going to have the product of this reaction. And actually, I need to draw OH in blue, right, because it comes from water. And of course, the catalytic side chains will be regenerated. So aspartic acid will be back to deprotonated state. And glutamic acid will be back to the protonated state. And will be ready for the next round of catalysis.